welcome to my classroom. Continuing with our topic on soil water, today we will discuss unsaturated movement of water in soils. As already told in my previous lecture that water can move in the soil either under saturated conditions or unsaturated conditions, or it can move in the soil as in the form of vapor, what we call as vapor flow. So we have basically three types of movements in the soil. One is saturated water movement, another is unsaturated water movement, and third is vapor flow. Vapor flow, in fact, water in soil in the form of vapor moves so slowly. This movement is so slow that this is almost negligible. So we ignore this. Most of the time, this unsaturated movement of water in soils is very common, even as compared to saturated movement. As I say, under natural conditions, it is seldom that soil may be saturated. Almost it is everywhere soil is unsaturated. Even if I say that you have a paddy field which is inundated with water, but immediately below 5 centimeter you will find unsaturated conditions of water in soil. So, in nutshell, this unsaturated movement of water in soils is more common than saturated water movement. At the same time, this is very important phenomenon in soils. Now you will ask why. Before that, let me tell you that what is this unsaturated zone of soil. You know that supposing this is your ground profile and here this is soil surface, and at one depth we have water table, and below this water table is basically the saturated zone, isn't it? So I should say it is the saturated zone. So immediately above this water table we have an unsaturated zone. We also call this as Vadose zone. Vadose or Vadose, I don't know how to pronounce it. It may be pronounced differently at different places. Vadose zone. Now this zone is very important for us. First of all, although the water content, this water content, whatever water comes into the soil, infiltrates into the soil through rainfall, it is stored in this Vadose zone. Or even water table, it may go high depending upon the recharge of groundwater source. But the question is, if we talk of total fresh water available on this earth, only 0.5% is being stored in this soil. But this 0.5% water stored in the soil, what we call as groundwater source, this is very important from hydrological point of view. We have a water cycle, we have hydrological cycle. For this Vadose zone particularly plays a very important role. So first of all, it provides us with a continuum of water, and then you have first of all saturated zone or water, then unsaturated zone, and then you have atmosphere over here. This is atmosphere. So it is basically a continuum between unsaturated zone and water or saturated zone. So it is connecting soil, atmospheric you can say interface, and underlying this Vadose zone is your saturated zone. So now this saturated zone, it contains only water and soil particles, but unsaturated zone, it contains soil, water, as well as air. That means all the three phases: air, water and soil, or you can say solids, liquids and gases. Then this zone, it stores water. Along with water, it stores nutrients also, and that's why it is very important for the biosphere. All the vegetation, all species of plants, even some of the microbes, many microbes, Even some animals also, large small animals, they live in this biosphere, that is in unsaturated zone. They find their food in this zone. So it also stores small fraction of fresh water along with air, so that's why it plays a very important role in the hydrological cycle, because it is controlling, the saturated zone or water table. It is also controlling the evaporation of water from the surface of the soil. And hydrological cycle cannot be complete until and unless evaporation takes place. So whether it is from the surface of soil or from water body, but this evaporation process is an important component of hydrological cycle. So this Vadose zone or unsaturated zone, it controls replenishment of groundwater, because we generally extract groundwater, then it goes down, then rains are there, so then it comes up, it gets replenished. So this is because of this unsaturated or Vadose zone that water moves into the soil. Water moves in vertical direction, in horizontal directions, and in upward direction also. So secondly, it controls the process of evaporation also because it's not only in water cycle or hydrological cycle that evaporation is important. Evaporation is also important for the formation of saline soils, for the formation of alkali soils. So that's why evaporation is very important to us. And at the same time, we can say it is the zone of human activity also. Why? Because it is this zone which is being cultivated by the humans, by mankind, for growing different types of food crops, fruit crops, vegetables. And at the same time, this zone is also very important for disposal of organic waste. Whatever organic waste you have, what is the waste of animals and plants that goes into the soil, it gets decomposed. That waste is actually the food for the microbes. The microbes eat upon that food. So this unsaturated zone in itself is a biosphere, contains billions, trillions of microbes which feed on the organic waste, and ultimately they convert they result in the formation of a cycle, another important cycle, what we call as carbon cycle. So if in nutshell, if I say that this Vadose zone is not only important for carbon cycle, water cycle, but also for carbon cycle, even nitrogen cycle or other cycles, sulfur cycle. For all the nutrient cycles along with water cycle, this unsaturated zone or Vadose zone is very, very important. And it is in direct atmosphere with the atmosphere or the gaseous phase. So if I say that movement of water, whether it is replenishment of groundwater, whether it is evaporation process, it is all dependent upon how water moves in unsaturated zone or Vadose zone. So now we will study the mechanism of this unsaturated movement of water. On this side, I have drawn a diagram. Don't get this is not a complicated diagram. No need to get confused. I'll later on come to the practical aspect of this diagram. This is unsaturated soil zone over here. Just like in case of saturated, or in Darcy's law, it was the saturated bed of soil or sand, which was used by Henry Darcy to explain the saturated movement of soil. The only difference is there. Here, this soil is unsaturated. This is point A, point B, water moving from A to B or B to A. So we have tried to show the negative hydrostatic pressure, because in saturated conditions the water movement was under the influence of positive hydrostatic pressure or positive pressure potential. Now it is unsaturated zone, and here you can see these dark, this is basically the ceramic plates, semi-permeable plates, through which the water moves under controlled conditions. And because the movement of water over here, this is simply the Marriott arrangement. So because of the Marriott arrangement, we have shown the negative hydrostatic pressure from A up to this point. The negative hydrostatic pressure is H1. That's why we call it as minus H1. From B to this point, this is minus H2, then this is the reference level. So the distance between A to reference level is Z1, from B to reference level is Z2. Both the values are positive because you know that the points above the reference level, they are taken to be positive, at the reference level 0, below reference level negative. Now if again following the same, you know, Darcy's law, if I say that what is total soil water potential at A, so this will be again your metric potential plus gravitational potential. Now the difference is that in saturated movement, instead of metric potential, it was pressure potential. Now here it is gravitational potential. It was same. Gravitational potential was there also. In unsaturated, again the gravitational potential is there. So now what is total soil, metric potential at A? It is minus H1. What is gravitational potential at A? It is Z1. It should not be minus, sorry for that. So it is Z1. Metric potential plus gravitational potential. Metric potential minus H1, gravitational potential Z1. Similarly, total soil water potential at B, then B, this is P point, minus H2 plus gravitational potential, that is Z2, from B to reference level. So if I say what is difference between the total soil water potential at 2 points A and B, so it will be minus H1 plus Z1 minus H2 plus Z2. So this becomes minus H1 plus Z1 plus H2 minus Z2, or you can say minus H1 minus H2 plus Z1 minus Z2. So this is difference in total soil water potential at between 2 points A and B, and if I divide this difference in total soil water potential by L, L is basically this distance between A and B. So now it becomes difference in total soil water potential per unit length of the soil column. So this will become the hydraulic gradient. And you know the Darcy's law, what Darcy's law says? That flux, that is centimeters per minute, this is equal to, or you can say the flux could be volume of water per unit cross section area per unit time. Okay, so this will be the product of K and hydraulic gradient. Now K is hydraulic conductivity, you know it. Now the difference over there is that earlier it was K sat, what we call as K saturated K. This was Darcy's law under saturated water movement conditions. Now here soil is not saturated, hydraulic conductivity, it becomes a function of metric potential. It's a function of moisture. Let me better initially say it is a function of theta. Now it will not be K sat, it will be K theta. Now I'll come back to this K theta, what happens to hydraulic conductivity under unsaturated conditions. So this becomes equation. Now this dependence of hydraulic conductivity on soil water content means higher the soil water content, more will be the hydraulic conductivity, and vice versa. This was given by Buckingham in 1907. He gave this idea that he was first to say that under unsaturated conditions, hydraulic conductivity is dependent upon moisture or it is dependent upon the metric potential. So that's why we call this as Darcy-Buckingham equation. So if you know the metric potential at A, metric potential at B, gravitational potential at A, gravitational potential at B, distance between A and B, you can find out hydraulic gradient multiplied by hydraulic conductivity at that particular moisture content in the soil. This will give you the flux, that is the amount of or volume of water moving per unit of time, per unit cross section area, per unit time. What we call this as velocity units, centimeter per minute. So now here the difference between what difference is there between saturated and unsaturated, soil water movement. So first of all, just take a cross section area of matrix, what you call as soil solids and soil pores. Okay, these are your soil solids. Then this is pore space. The macro pores, they could be occupied with air. Say this is a macro pore, this is a macro pore over here, say it's a macro pore over here. Okay, rest of the pores, they are filled with water. Okay, now if this is your point A, this is point B, if this would have been a saturated soil, then there would not have any air bubbles over here or air spaces. Water would have straight away moved from A to B. Now here when water moves, it has to go like this, then it will go like this, then it will go like this. So if I say that the actual distance traveled is A dash B dash, say this is A dash B dash, and the real distance between A and B, this is AB. So that means now the soil matrix has become more tortuous. We call this as tortuosity. So tortuosity means the distance actually traveled by water to, this will be the real distance divided by the distance traveled by water. So ratio of the two is called tortuosity. So first difference is when soil becomes unsaturated, the movement of water is curtailed because of the tortuous nature of the soil matrix. So there is no continuity of water in the soil for the movement, for its movement. Second thing is K, hydraulic conductivity of unsaturated soil is always smaller than K sat, because of two reasons. One is tortuosity of the soil. Second is when all the pores are filled with water, there is a continuous column. That's why the tortuosity is less, and that's why the K is the maximum value of hydraulic conductivity is maximum. But as the soil becomes unsaturated, the macro pores, they get occupied by soil air, then soil becomes tortuous and the water has to travel much more distance, and at the same time when water has to move like this along the soil solids, there is attraction of water molecules by the soil solids, and once this attraction force is there, then the velocity will decrease. So this is another reason that always unsaturated soils, they have lower hydraulic conductivity than that of K saturated, and you will be surprised that sometimes this is lower by millionth of saturated hydraulic conductivity. You cannot imagine that there is sharp drastic reduction in hydraulic conductivity of unsaturated soils, and again it is dependent upon theta. It's a function of theta, because if water content goes on decreasing from the soil, that means air will increase. More the air, more will be the disruption, more will be the lower will be the movement of water in the soil. If water content increases, then air bubbles will be removed, so there will be more continuity of water in the soil, and it will be easy for the water will be moving faster from one point to another point in the soil. So third thing is that this hydraulic conductivity may not be uniform. Vertically, because the soil has different layers. It is seldom that you have a homogeneous profile of soil. Soil may be quite it may vary in texture from one layer to another layer. And what will happen to K? Let me show this with the help of a diagram. That if this is a soil profile, here you have soil depth, and upper portion of this soil profile is coarse texture and lower is fine texture. Okay, now this is your metric potential, oblique you can say it is theta. Now a particular water moving in the soil, when it reaches the boundary of coarse and fine textured soils, it will stop over here. It will go like this. The moisture content will have to increase, or in other words, metric potential will have to increase, and only then, if this is your water table, this is how. So first water will stop over here, more water will gather over here, because in coarse textured soils the water is not held by a greater force as in fine textured soil. So that is why in order to the water to enter from coarse texture, that means from macropores into the micropores, the suction has to increase, because in fine textured soil it is held with greater suction, greater tension. So that's why the tension or suction increases, and then ultimately as the water content increases at water table, when it joins the water table here, metric potential will become zero. This is, on the other hand, if you have, say, the reverse case, you have a fine textured soil in the surface and coarse textured soil over here. Now here in the fine textured soil, water is held with a greater force, so this tension will be higher over here. But when it reaches towards the boundary, it cannot enter into the micropores until the suction gets reduced to a certain value, and again it joins the water table. So here the suction has to reduce, so that the required suction at which the water can enter the macropores, that is reached, only then movement of water will be there. So this is difference that hydraulic conductivity, because if psi m is going to change, K hydraulic conductivity unsaturated soil is a function of theta, or it's a function of metric potential. So here in unsaturated conditions, this metric potential plays a role not only for creating a hydraulic gradient, but also for affecting the hydraulic conductivity of the soil. This is very important point. So here, because this with increase in suction like this, with increase in suction over here, when suction will increase, then hydraulic conductivity will decrease, because with increase in suction the moisture content will decrease and hydraulic conductivity will also decrease. So this is how the unsaturated water movement takes place. Now I'll just explain this process, that if under real conditions you have to find out the movement of water in unsaturated conditions. So I'll simply explain that. Let this be your field. This is your field, this is a boundary over here, this is field boundary over here. Okay. Now this is the surface of soil. You want to know that, you want to measure total soil water potential at A, and you want to know that whether in that particular condition water is moving from A to B or B to A. The soil is unsaturated. Let me say it is Vadose zone, unsaturated soil. Now the same thing over here. We have to, we require from the equation, Darcy-Buckingham equation, we require two things. One is metric potential at A, metric potential at B. So you very well know that how we measure the metric potential. We measure the metric potential with the help of a device called tensiometer. I have explained the working of tensiometer in my previous lectures. So what we will do, that we will install a tensiometer over here. This is ceramic cup. So ceramic cup, center of the ceramic cup, it should coincide with point A, and here you have, you know, this tensiometer. So you have these we are measuring in bars. So you have installed one tensiometer at A, and similarly you will be installing another tensiometer at B. Again, this is the ceramic cup. Now, whatever will be the moisture content over here, depending upon that, you will get the metric potential. So this will give you minus H1, this will give you minus H2. Simple, very simple. You have installed the tensiometer, you are getting the value of this. And again, you know the distance between A and B. Let it be L. So you know L. Now Z, supposing that you have this reference level, soil surface as reference level. Now distance between, say it is 5, 10, 15, 20. Now this is at 10 centimeter. So this distance between reference level and A, this is your Z1. So Z1 is now, since it is below reference level, so I will say it is minus 10 centimeter. And Z2, this is distance, this is point which is 20 centimeter below the reference level, so this will be minus 20 centimeters. So very simple. Now you know the H1 value, you know H2 value, you know Z1, you know Z2, you know the value of L. Substitute in the equation. Then you have to measure rather, I should say, or you should have a record of hydraulic conductivity of this zone, of this layer. That hydraulic conductivity at a particular moisture content. So this will give you K theta times total hydraulic. So this is how practically you can do it. In saturated soil, you can simply do it by, instead of tensiometer, it will be a piezometer. Install piezometer at A, install piezometer at only if the soil is saturated. And then again, you can choose reference level anywhere. I told you earlier also, because it is not the magnitude of reference level, it is the difference between the reference level, or you can say difference between the gravitational potential at 2 points, that matters to us. So whether you choose reference level over here or over here or even over here, doesn't matter. So very simple, using this equation you can find out whether water will move from A to B or B to A, and in any case what is the flux of water using this equation. Very simple. I hope the things are clear to you. Thank you very much.